So today I will talk about the connection between pseudorandomness and property testing, and how we can use both to basically establish limits on both and basically learn what are the limits on pseudorandomness and property testing. Okay, doesn't work. Okay, there we go. So why do we care about randomness? Well, pseudorandomness is essentially about randomness, and randomness is important for many things, such as cryptography, for communication, benchmarking. And in the classical, you care about Monte Carlo simulation. There, you always basically randomness or even quantum randomness. Now, how do we actually generate randomness? Well, in the classic case, it's relatively easy. You just basically randomly select a bit 0, 1 by some kind of random process. Now, in the classical world, it's a bit more complicated because like the quantum true randomness would be, let's say, a H-random state or a H-random unitary. So to visualize this, basically, you would kind of draw uniformly from the H measure, uniformly from the space of states or unitaries. For example, if it's a qubit, it would be kind of drawing uniformly from the Bloch sphere. But if you scale up, let's say you want to draw a uniform state from a high many n qubit state, you will find out this gets very complicated. In fact, it scales exponentially. So if you want to sample an n qubit state, the resource you need is exponentially in number of qubits n. So basically, the bigger you are, the more difficult it gets, and it's technically or practically impossible to generate hard randomness, let's say, on a quantum computer. It's not efficient. So if you want to generate quantum randomness, this is something we cannot do in any practical sense. So to solve this, you can harness concept from what people harness concept from classical idea, namely the idea of kind of having this to generate randomness in a computational point of way. So we have suddenly, this was introduced very nicely by Tom Yuki on Monday. We have, for example, in the classical world, we have something called a pseudorandom generator, which is kind of an object that generates pseudo-random bits by using a small random key k, which is much smaller than the number of bits that you want to generate, and you use a deterministic algorithm that produces the random-looking bits. Now, this algorithm is deterministic, obviously, but by implying a random key, the output will look very random. And for example, you know this in a very practical sense. Let's say if you program in Python, you use this many times. You use, for example, you call numpy.random, and then you can print out random integers or random bits or random floats, whatever you like, and it just spits out many random-looking numbers. And the randomness of these numbers is guaranteed, assuming some kind of computational assumption. So you need some kind of underlying assumptions, and the most fundamental assumption in classic crypto is the existence of one-way functions. If one-way function exists, then we know that these random numbers will look random to any efficient algorithm. So any efficient algorithm will think these numbers look just like true randomness, although they're actually generated by some kind of algorithm. Okay, so this is a way of generating classical randomness, and now you can transfer this concept into the quantum world by the concept of quantum pseudorandom states. You heard about this on Monday. So the idea is we have now an ensemble of quantum states. We now go into the quantum world, and they're parameterized by some kind of key k. And we demand two conditions on this set of this ensemble of states. First, it should be efficiently preparable by a quantum polynomial tile algorithm. And if you take a polynomial number of copies of these states and you run some kind of efficient quantum polynomial tile algorithm on it, it will be indistinguishable from H-random states. So if I give some kind of algorithm or any quantum computer many copies of these pseudorandom states, it will say they look just like H-random states. It can't tell them apart. For them, it looks the same. So they kind of mimic H-randomness, but for any efficient algorithm. But now we can prepare them in an efficient manner, right? Because H-randomness, as I said before, takes substantial time. Now we can do this efficiently. Again, of course, we need some kind of price to pay, and the price to pay is you have some kind of underlying computational assumption we need. But it turns out they're actually weaker than classical pseudorandomness. So we can actually, well, it has been shown by question that it's potentially possible to generate pseudorandom states using assumption that they're weaker than one-way function, but you can use even some weaker concepts and still get PS. So it means even if maybe classical pseudorandomness doesn't exist, quantum pseudorandomness may still exist. So you can basically apply some weaker assumptions. Now, how do we actually, let's say you go back to practice, how do we actually make a PS, a pseudorandom state? Well, people proposed many different constructions, first one back in 2018. For as a kind of demonstration, let's look at this one. This is called the binary phase state. So the binary phase state is like you take a computation based state X, and then you sum over X. And for each commutative basis state, you now assign a phase plus or minus 1. And the phase plus or minus 1 you assign by a pseudorandom function. So this function will either spit on plus 5, will either assign a phase plus 1 or minus 1, basically choosing this function, which is parameterized by this key k, and basically randomly assign a, basically not randomly, but according to this function, it will assign a phase plus or minus 1. And one can show that this binary phase state is a PAS, so it's indistinguishable for any quantum algorithm, efficient quantum algorithm from H-random states. Although it actually looks nothing like a H-random state, right? It doesn't really look like drawn randomly for the H-random space. Yet you can show that this is actually indistinguishable for H-random states for any efficient algorithm. Okay, and the nice features is, first of all, one can show that these states can be prepared in polylog depth. So the circuit depth is only polylog. So this is quite amazing because H-random, as I said before, takes exponential depth. Now we basically get a doubly exponential advantage in circuit depth to prepare them. So we can generate what looks H-random in our extremely short depth. And secondly, it's also interesting to note, this will come important later, if this thing is real valued, right? There's no complex phases here. It's just plus and minus signs. Extremely simple. In particular, there's no complex numbers. Like quantum mechanics normally has complex numbers. Here, there's none. Okay, you can also play the game again and go to and define similarly pseudorandom unitaries. You heard of this before. They can be efficiently implemented, and they're indistinguishable from H-random unitaries for any efficient algorithm. Now, again, we can ask, how do we actually make one? Now, it turns out this question is a bit more complicated. In fact, it took 6 years to solve it. It was only solved recently in January by Schuster and Co. And why it's complicated, I will now elucidate. Let's take the most naive idea how to make a PRU. Let's say because we know how to make PAS, right? So let's just take the state preparation routine of PAS and make it into PRU. And would that be a PRU? Let's say, for example, if you take our binary phase state, right, with this plus and minus signs, and basically it can be prepared by basically a unitary applied on a product state. And this unitary is like basically just a unitary that randomly, or not according to the function, assigns the phases plus or minus 1. Now we could ask, can this thing be a PRU? I mean, this thing, obviously, the state prepared by this unitary is a PRU, but is the unitary that prepares a PS a PRU? One can think maybe yes, right? I mean, it's able to generate PS. Why not also prepare? Is it also a pseudorandom unitary? So we now see in a minute whether or not this is actually a PRU. But we can now ask more the question like, what are the fundamental limits needed in order to be a PRU? Like, what is the requirements? What is necessary in order to become a PRU? Can we establish somehow some limits on that? And for that, we need another concept, which is called property testing. So the idea is very simple. Let's say I give you a state psi, and now I want to check, does the state psi have a particular property Q? To give a very concrete example, let's say we want to test the entanglement in the system, like how much non-local correlations are in the system. Now, if the state is pure, we can actually test this. So we can, if you are given experimentally, let's say someone gives you a state psi, you can actually make a test and say whether the state is separable or whether the state is entangled. And you can do this efficiently. For example, we can just using something called a swap test, like this. And this test basically tells us, is the state entangled, or is it separable, or is it not, or is it highly entangled? So we can separate these two cases. And this is what people call property testing. We can check for the property of entanglement. And basically, you can use this, for example, to distinguish states with low and high resources. And one can do this not only for entanglement, but people propose similar testers for other properties, which are important, other important resources of in quantum. For example, people propose such tests for magic, which is the degree of not being a Clifford state. And for coherence, which is kind of how much superposition does a state have or a unitary have, and also imaginarity, which asks me the question, how much complex amplitudes are in the quantum state or the unitary. So these are all important resources that people need to do quantum computing or quantum communication and so forth. It's one of the most important resources for quantum. And using this, we can now establish limits on what properties PS and PRU need. So first of all, H-random states, as I said before, they're very complicated. They need a lot of resources. In particular, you can show they have near maximum entanglement, matching coherence. In fact, it's linear. Whereas now we know that there are efficient property tests that are able to distinguish low and high resource states. In particular, for entanglement, magic, and coherence, we know efficient algorithms that can check whether a state has less than logarithmic, let's say, entanglement, and linear entanglement. So you can separate these two cases efficiently. And that means basically if we have a state which has less than log entanglement, then there is an efficient test to distinguish it from high random states, which have a lot of entanglement. So therefore, they cannot be a PAS or a PRU. So in order to be a PSU, a minimum condition is that they need at least polylog entanglement. Because once it's polylog, there's no efficient way, there's no efficient test that can distinguish them, or we don't know any efficient test to distinguish from entanglement and magic or coherence from high random states. So this basically gives us it's all screwed up here, but yeah, you can still see it. So this gives us basically a lower bound on the resources needed in order to prepare PS and PU. In fact, for entanglement, magic, and coherence, one can show that you need at least polylog, entanglement, magic, and coherence in order to prepare them. This is the minimum requirement due to property testing. And for example, we show that that for PS and PRU, not having low coherence implies they must not be sparse. And also for PRU, there is an efficient test for unit test, there's an efficient test to check for complex numbers, so whether a state has a complex numbers inside or not. And this directly implies that the unitary we talked about earlier, right, that assigns random plus and minus phases cannot be a PRU, right, because it's obviously sparse. And also it has no complex numbers, so therefore it must not be PRU. This is quite interesting because this implies also that making PRUs is much harder than making PS. There's more stringing conditions. So this explains again why making PRUs was so more difficult than just making PSs. Also a fun fact, while PRUs cannot need complex numbers, this is not the case for PRS. So pseudorandom states actually can be real valued, right? We had this binary phase state before that's completely real, but this is indistinguishable from high random unitaries, high random states. So this actually now allows us to put a bound on property testing. So using this existence of the state, we can now show that testing for imaginarity of states is inefficient. So you cannot check whether a state has complex or real numbers, like they look the same. So that's quite interesting because testing basically unitaries, you can efficiently test unitaries for complex numbers, but for states, this is not possible. Like you can't check whether a state has complex numbers or real numbers. So some of this resource imaginarity is testable for, not testable for states, but you can efficiently test it for unitaries. So there's a weird gap between the two that we don't find in any other resource. So this is quite curious. Okay, now we can ask another limit, namely, when we want to run actually something on a quantum computer, we always have to deal in the end with noise. Now we asked, are PS and PR robust to noise? Let's say, can we run a noisy quantum computer? And we showed basically this is not possible because you can easily see that if a PS or PU is subject to even very small noise, one or poly n noise, there is an efficient algorithm to distinguish from high random unitaries, which are inherently pure. For example, you can use the swap test. So what this implies is that as soon as we have even a little amount of noise, there is no PRUs stop being PRUs and PS stop being PS. That means PS and PRU are not possible, let's say in a NISQ or early fault tolerance, where we expect to have a bit amount of noise. In order to actually prepare them in practice and actually prepare them in their full glory, we actually need to go to a limit where we have very good error correction and we can remove all the noise down to an exponential or negligible amount of level. So this puts very hard and stringing conditions on how to actually prepare them in practice on a quantum computer. Okay, but now we can ask, maybe that's too disappointing. Is there a way of somehow generating pseudo-randomness in a way that is robust to noise? For this, we introduce something what we call a pseudorandom density matrix, which is a generalization of the pseudorandom states to mixed states. So we can immediately generalize this. First of all, we generalize high random states. So high random states is like drawn uniformly from the space of from quantum states. We can generalize to what we call the generalized Hilbert-Schmidt ensemble, which is basically just high random states, but you trace out m qubits. So you just check out m qubits, and then you get an ensemble. And we now say that pseudorandom density matrix or PADMs are, first of all, they're efficiently preparable. So meaning you can show you can easily prepare them, for example, taking a PS pseudorandom state and tracing out m qubits. That gives you a efficient way to prepare them. And second, they're indistinguishable from this generalized Hilbert-Schmidt ensemble. So you can't tell them apart. And obviously, if you take the case m equals 0, we don't trace any qubits, we come back to PS. And if you trace a polylog amount of qubits, in fact, we can find that PADMs are indistinguishable for any polynomial time algorithm from the maximally mixed state. So they just look like completely trivial states. But the nice thing is that in this regime, PADMs are actually noise robust. Namely, we can show that they are robust to unit and noise channels. So even after applying unit and noise channels, a PADM is still a PADM. So they basically are, this is a definition that it remains robust to noise. And in fact, it applies to arbitrary noise channels. And we can actually directly apply this in practice. We, for example, we can use this to construct noise-robust EFI pairs, which we learned about on Mondays. This is basically a very important cryptography primitive. And we can show that using this PADMs, we can construct PADMs which can tolerate more noise than the threshold of the service code there. So they're extremely robust. So they can tolerate extremely high levels of noise and still be functional EFI pairs. So this is something that could be realized directly on today's quantum computers. So this is something that's very interesting to actually make first experiments in quantum crypto. Okay, so I come back now to this idea of the resources. So how much resource do we need to actually prepare pseudo states? As I mentioned before, harm states need a lot of resources, but it's like how much entanglement, matching coherence is like linear. But is this actually needed also, let's say, for pseudorandom states, or can we go lower? Like, do they need the same amount of resources as harm states, or can we push this much lower? In fact, yes. So this was shown by Scott, Ernst, and Koh. They do what they call quantum pseudo-entanglement. So these are like states. Pseudo-entangled states are states which have a lower amount of entanglement. It's like polylog across every bipartition. So they have like they have extremely low entanglement, relatively low entanglement, but they're indistinguishable for any efficient algorithm from states with linear amount of entanglement. So you have like states which are kind of nearly area law, yet for any efficient algorithm, they look like volume law, highly entangled states. So using something that is extremely low entangled, you can mimic something that has extremely high entanglement. So with low resources, you can pretend to be high resources. So this is a very nice kind of way, like pretending to be more than you actually are. And we generalize this concept now, what we call pseudo resources. So the idea is that we have two ensembles, which are indistinguishable for any efficient algorithm. And the first ensemble is like a high resource ensemble with, let's say, f of n resource, and the second is a low resource ensemble. And we now ask, like, what's the maximal largest possible gap between those two? So like basically, what's the maximum gap between this f of n, the largest resource possible, minus the smallest possible resource g of n, and they still remain indistinguishable. And we can basically show that we can basically map this out for pure states. And basically we find that for, let's say, entanglement matching coherence, you have a gap of linear versus polylog. So this is for pure states, the maximal gap between those two. So basically by polylog, let's say you can have states with polylog coherence, yet they look like states with linear coherence. So you can basically use very low resources to mimic high resource states. Interesting, that doesn't work for imaginarity, because I mentioned earlier, real states are already PS. So basically, you can basically mimic high complex numbers by using basically real numbers, which is quite funny. Now we can ask, is this actually the best you can do? Right? Because there's still this kind of gap between polylog and linear. Like, what can we do actually better? And in fact, you can, by going to these PADMs, these kind of mixed states, we can actually get better pseudo-resource gaps. For pure states, we have this gap, as I mentioned before, for polylog versus linear. This is the best you can actually do. You can show this is optimal. But if you now go to these PADMs, these kind of mixed generalization, you can actually get much bigger pseudo-resource gaps. So in fact, we show that PADMs can have a gap between linear, the maximum resource, versus 0. So basically, you can have states which are like completely trivial, the maximum mixed state, but they're indistinguishable from resource state with near maximal resource. So basically, by bringing in states with basically 0 resource, you can pretend to be high resource state, and vice versa. Like you can have high resource states, which you can mask as trivially maximum mixed state. So you can efficiently kind of hide resources completely from sight. So anyone who checks will say like these are like low resource states, but they actually contain a lot of resource. It's a very, very good way of hiding your resources in plain sight. And this has actually very strong implication on property testing. And namely, what this implies is that testing entanglement matching coherence is in general inefficient. This is quite important. So that means basically, so why is this the case? Because we have these ensembles which are indistinguishable. There must be not any property test for this, right? Because else these PADMs couldn't exist with this pseudo-resource gap. So this basically implies that in general, these resources like entanglement matching coherence, although they're like the key properties of quantum computing and quantum information, right? That's what we care about. These are like the key properties that heavily affect the structure of quantum states. Yet there's no way to tell them apart. Like we cannot say whether a state has high or low resources in general. Like there's no experimental way to distinguish those two. So they're not really efficient observers in nature. They're more like, constants we in general cannot tell apart. And we showed that this depends heavily on the purity testing efficiency. So for pure states, they are efficient tests to test for these resources. But once you go to low purity, we don't know how to test them anymore. And this also has an interesting implication. I'm not going to more details in this, but basically we show all that black box resource distillation, where you basically distill resources without knowing the state, is inherently inefficient. You can't do this in practice. Okay, so if this already come to conclusion, so I showed you basically there's some limits of property testing and PRUs, and basically you can use PS and PRU to states to basically give limits on property testing, and property testing gives you limits on the PS, so they have a very nice interplay. I showed you about the pseudo resources that we can mimic low resource states and high resource states, and we can basically completely hide resources from site completely by using these PADMs, these mixed states. And I showed that property testing is in general inefficiency. And there's not many future works, just some ideas. You can have asked whether there's other noise robust application of pseudorandomness that we could realize maybe in the near term or in early fault tolerance right now. Or we can also ask what other properties besides these resources are actually important for pseudorandomness and which are not important. So we're going to try to map out, because there's many more resources of this kind, which one more we can map out. And there's many more things. So this is very exciting. And with this, I thank you very much for your attention. And yeah, thank you very much.
Hi, thanks a lot for interesting talk. I just wonder how your results, the sparseness and the complexity requirements relaxes if you just want T design instead of like true Harman randomness.
For T design, if you have a two design, so one design doesn't need any coherence, like maximum mixed state is already a one design. For two designs, I think you need at least normally volume law entanglement, volume law coherence, everything. Like anything needs to be linear for two designs already. So anything above two designs needs a lot of coherence, magic, and so forth, and entanglement.
Okay, and also how does your result generalize to general like qubits, any dimensions?
That's a good question. So there was one study on the limits. So yeah, it's not clear yet. I mean, I think the bounds, how much resource needed to generate, may be lower for qubits. So there's a work by Zhao. I'm not sure if he's in the audience. Yeah, you can ask him. He's the expert on this. So he studied qubits, so he knows more. So you should ask him afterwards.
Thanks.
But it's an open question. So it's not clear yet completely.
As a question?
Okay, thank you for the talk. I am a bit confused about your definition of robustness. Mm-hmm. So when you first mentioned robustness in your talk, so do you apply noise only to your pseudorandom state, or do you apply noise both to pseudorandom and to the true Haar state?
It's only applied on the pseudorandom state itself. Because if you apply both in Haar and the pseudorandom state, then you apply the same noise in both, right? So they would still remain indistinguishable.
Okay.
So the idea is that you apply it only on the let's say on the state, and then you ask, is this still distinguishable from a Haar random state? And obviously it's not, right? Because now you can use the swap test to distinguish it.
Okay, thank you.
Yeah.
As a question? So I have also some question. So for pure PRSG, from pure PRSG, you can construct money and one OIST generator, because there is some verification algorithm for pure PRS. So if you have a key, you can verify that this state is psi k.
Yes,
and for mixed PRS, can you verify that? Is there any verification?
The verification. That's a good point. Yes, so because we define via the tracing out, right? So in order to verify, you actually need the traced out part back in, right? You need the traced out qubits to verify. But there is an alternative definition of PADMs where you could do verification efficiently using the key. But I disagree, like with this definition you can't, but there's an alternative definition you could use that is verifiable.
Yeah. So you don't know how to construct, for example, private key from this mixed PRSG?
I said with this definition you can't, but there's an alternative definition where you could actually do it. That's pretty much equivalent to this one.
How can you verify mixed state?
So you can do some kind of randomness injection. I can tell you about it if you want.
Yeah.
Quick question: is your result for your gap for entanglement? Is it a result or is it a conjecture?
Sorry, that's a conjecture. Yes. I was unclear, but this is so far conjecture. because we didn't manage to actually compute. But I think it's likely true because we can show it for states which are inefficient to prepare. We can actually show this exactly, this gap.
Okay.
But for we don't find for the PS, we didn't manage the calculation. But
okay, you didn't get any. But did you get anything? Or
no, because it's quite difficult to compute the segments.
I see.
But there are computations for states which are inefficient. For those, you can actually show this gap exists.
Right.
So the efficient part is still lacking. But I think it's very likely to be true because I mean there's many indications it should be the case. But I agree, it's a conjecture. So, but yeah, if someone expert on how to compute it, this would be very much appreciated. How to actually compute this explicitly. It's a bit trickier, but it's a technical problem, I think.
Hi, thanks for the nice talk. So I just have a very minor question about the unital noise channel, right? Is it a global noise channel or is it like single qubit or small local qubit channels?
The noise channel we use is a single qubit channel, but it doesn't matter. You can pretty much use any noise channel you want.
Okay, and
for any noise channel you will find pretty much the same results. It doesn't really matter what kind of noise you choose. We just use this for convenience. Because the most common noise model, but you will find the same result for any noise channel.
And do we know anything about a non-unital
one? You will find the same issue for non-unital noise because normally non-unital noise will again, you can probably find some kind of POVM that distinguishes them. Let's say if you use amplitude dampening, again, you can find some POVM that will distinguish them efficiently.
Okay, thank you.
The question? So here you say that if you have some noise, you cannot construct a PRU.
Yes.
But on the other hand, some people believe that random circuit is PRU. So do you mean, so for example, can you say that if you have a random circuit and if you get some part of this output, this cannot be PRU or something like that? Because if you have some random circuit and if you trace out some of them, maybe effectively you apply some noise. But according to your result, this shouldn't be PRU.
No, not by averaging at least. I mean, you could do some kind of post-selection. Maybe then it could still be made PRU. Like if you measure some part of the system, then you can generate a random on the left. But this is not an efficient process because it requires post-selection. So, so as soon as you add some noise, whether by tracing out, I think it's not a PRU. I mean, it will be something else, right? You could define some kind of, let's say, random channels or something that may still work. But I don't think it will be unitary, right? Because unitary requires perfect pureness. Like you need to be pure up to extremely low noise levels.
So maybe you could show that some specific construction of PRU from random circuit is not possible.
I mean, random circuits with noise. And if there's no noise, it's fine, I think. But yeah, once there's noise, you have a problem.
Yeah, but maybe we can discuss. Other question? Okay, if not, let's ask the speaker again.
Yeah.
Okay, so let's start the next talk. Next talk is by Shivan about arbitrarily connected local random circuits from unitary designs. So please start.
Well, thank you for giving me the opportunity to talk here. Today, I'll talk about what are random circuits and what is this property of theirs called unitary designs, and how deep do the circuits need to be to get to those properties, right? So, okay. All right. So just to clarify some definitions, because people call many things random circuits, and it is going to be important to interpret the new results that have come out in the past 8 months or so. What I'm going to be calling a random local circuit is you'll have n qubits, and you have 2 qubit gates, or n qubits and 2 qubit gates. And there's something called the architecture, which is the connectivity of these qubits. So which 2 qubits can have a gate acting on them. And then what is going to be the local random circuit is I'm going to pick 2 qubits which are connected and then apply a random 2 qubit gate. So for example, the Google's processor is like a 2D architecture, and the one by USDC is also a 2D architecture. Just a concrete example, in 1D architecture has nearest neighbor gates, which are picked from the higher measure on U, Q square, where Q is the local language. Right. So why are we interested in these things? Of the many reasons, I'm going to focus on 3. First is they act as, so I'm also from the physics department. I understand this is more like a computer science conference, so I have some more physics sort of applications in mind. But random circuits act as models to describe how systems not in equilibrium reach equilibrium. And we can, these are analytically tractable models, so we can track how the entanglement changes in many body systems as the system approaches equilibrium. They also, random circuits also are examples of, well, they are the models for quantum advantage because of the random circuit sampling task. And then the third application is sort of originated in high energy physics. It's called complexity growth. I do not know the high energy implications of these things, but the basic idea is, and it works for any quantum many body system, the basic idea is there are quantities like complexity, which continue to grow for time scales much longer than the time scales at which normal quantities like correlation functions would saturate. So it's something that tracks your system beyond what normal thermodynamics quantity can. So random circuits are a case where we can actually prove that the complexity grows. So yes, a neat example of that. Right. So now what's unitary designs? So the way I'm going to describe this is through a random walk picture. So imagine the random quantum circuit is a random walk on the unitary group. So we begin on the identity element in the unitary group. And then with every gate that we apply in our circuit, it's like moving a step randomly on this group. And after t steps or so, we reach some final point. Right? This is one instance of a walk. So if we take many instances of such walks, t-step walks, we end up in different locations, and this is the distribution over the final points that we get. The question of unitary designs is how close is this distribution to the uniform distribution on this group. The uniform distribution is the high measure. Right? So why would you like to study the closeness of this distribution to the higher measure? Again, so taking those examples that we just discussed, for many body systems, many body quantum systems, we can get the time scales after which those correlation functions or some property of entanglement saturates. Right? So if our circuits have this property of unitary designs, and we understand the time scales or the circuit depth after we get this property, then we know the time scales after which our correlation functions saturate. In quantum advantage experiments, we can derive a property from unitary designs, which is called anti-concentration. And anti-concentration says the output distribution is neither too peaked nor too flat. It's somewhere in the middle, some sweet spot that makes it hard to sample from. And then again, if we can show that our random circuits form designs, then we can rigorously prove that the complexity grows. And this was achieved fairly recently, I think in the past 4 or 5 months or so, which made my task of making these slides harder and harder. All right, so just more concretely now, what is unitary designs? I think the previous talk hinted at some distinguishability measure. I just want to make this a bit more precise. We are comparing two distributions, one that we get from the circuit and one which is the Haar measure. If you want to compare two distributions, the natural thing to do is you compare their moments. So in this case, if this seems very cryptic to you, all this is saying is compute the kth moment of my distribution and compare it to the kth moment of the Haar distribution on the unitary group. And the norm that we pick, well, there's some ambiguity in that. So there are many norms that we can pick to compare these moments. Right now, I've written it out as a channel. I've written the kth moment as a channel, and that's why I use a channel norm. Yeah, just to remind you, this was the distribution that we are comparing to the uniform distribution. But there are other norms that one can use, or other notions of distinguishability that one can use. And one of those is called the relative error. So this is called an additive error. Epsilon here is called an additive error, whereas this, where phi is just this channel, this sort of an epsilon is called a relative error. So normally, this epsilon or this sort of an error is stronger than this sort of an additive error. But if we demand that the additive error is exponentially small, then that is stronger than the relative error. Right, so there are these little bit of intricacies in how you define designs. And it's kind of important when you're reading design papers to really understand what is the notion of distinguishability. Yeah, just to clarify, since both of those measures are really hard to directly compute, we never really directly compute them. What we work with is simpler notion of distinguishability. We vectorize our channels, and then we demand an exponentially small operator norm. So that is the operational definition of designs that I'll be working with, and I'll be showing what is this T, how large does this T need to be, given some architecture, what should this T be such that we get an exponentially small operator norm there. Any questions about the definition? Right. So why do we worry about these arbitrary architectures? Brandau, Harrow, and Horodecki already proved all of this for 1D architecture. Like, why do we care about arbitrary architecture? It's like a simple intuition that if you have more connectivity, you expect that perhaps your output distributions of your random circuits become some mess very quickly. As opposed to if you had less connectivity, you'll probably expect more gates in your circuit before you get to something which is hard to sample from. So since quantum technologies are becoming more and more powerful that allow for non-local gates, I mean, it would be nice if we had some rigorous results about how quickly, or what's the connection between connectivity and how quickly we reach hard to sample from distributions, or how quickly do we form designs. So before we started working on these things, this was the state of the art. This is not the state of the art, just to clarify. Many things have changed over the past 8 months, which I'll clarify in the end. But this was before October 2023. This was the state of the art, where the way to interpret this is a 1D local architecture just means one gate per time step. Parallel is when you squeeze many gates into the same layer. So really the circuit length is the circuit depth. Complete graph is all-to-all connectivity. And right now you should just completely object, and you should be like, okay, the best known result previously was that even on a completely connected geometry, it takes us more gates than it takes us on a 1D geometry. So clearly our results are not optimal. We need to do something better. In the end, just a spoiler, that is still not solved. Right? Even though all the papers that you have seen, that distinction between completely connected geometries and 1D geometries are still not solved. And then the last is d-dimensional Euclidean lattices, so just lattices. And it's not really a random quantum circuit in the sense that I defined it, but it's sort of close. I just put it up there. These were the geometries for which we knew how to form. We had rigorous bounds on the depths of circuits, after which they form K-designs. So what we did was we tried to generalize this to random connected graphs. Right? So if your graphs had some maximal degree, less than 38, those come out from some numerical calculations. But yes, if you have some arbitrarily connected graphs with certain maximum degrees, and if you want to form certain order of designs, then we had explicit constants about circuit length. Right? And our method sort of improved upon the 100-page proof of this previous result and made it into 2 pages. So that was also kind of nice. And then we also identified a class of connected graphs where we can also comment about the scaling in K to form K designs. So connected graphs with some bounded degree or certain logarithmic depth, they all form K designs in polynomial in n number of gates. And the K, the scaling in K just comes directly from the scaling in K for the 1D bounds. Right, so there were these 2 methods that we use. One's called the Kanabe method, and the other is called the detectability lemma method. Actually, how much time do I have? Okay. So, since I have enough time, I would go over some basic technique of how we went about proving these things. Just a big picture overview. So we want to find the error between the kth moments that I call the gap. And we want to find that between the distribution that we have after t steps and the uniform distribution. But convolving distributions is hard, so it would be great if you could just work with distributions that we get after 1 step of the circuit, which is what we can do. It's simple norm inequalities that lets you do that. And then, which is given the first point. And then if we show that this distance is less exponentially small, then we can infer what the t should be for the circuit depth. The way we do this is using some physics techniques of proving spectral gap lower bounds for Hamiltonians, local Hamiltonians, frustration-free local Hamiltonians. Turns out this object that you see here inside the norm can be interpreted as a Hermitian. It is a Hermitian matrix, and it is a Hermitian matrix which is a sum of many terms, each of which is a little Hermitian matrix, right? And so we can think of it in the physics literature that just goes by the name of two local Hamiltonian. The fact that it's frustration-free is a bit more technical, but yeah, it's a nice property that allows you to show what its what's its eigenvalues are, which is what we will be interested in. So the delta H is the second smallest eigenvalue of this Hamiltonian, and we use some physics tools to prove a lower bound on the spectral gap, delta H, and this depth then is bounded by this simple expression, where E is the number of edges in your graph. So if you could find a lower bound on this quantity, then you have an upper bound on the depth, after which you get T designs. So we had 2 methods in mind to prove these lower bounds on the spectral gaps of frustration-free Hamiltonians. The first method gives us these bounds for a fixed choice of K, and the second method gives us the scaling in K. Right. So I can go over the technical details, but maybe I should just probably give a big picture overview of what's happening in these details, in these methods. And the basic idea is to prove spectral gap lower bounds, you want to simplify the graph that you're working with. So instead of the connected graph, just take the spanning tree of the graph. And the Hamiltonian on the spectral gap for the Hamiltonian on the spanning tree just lower bounds the spectral gap that you are looking for. So operationally, we find this. And to do that, we use this very well-known technique of using detectability lemma and quantum union bounds. The way one should think about this is these are the matrix analogs of AMGM inequalities in usual algebra, where the spectral gap is like the arithmetic mean, and the detectability lemma, the right-hand side of that equation, is like a geometric mean. It's a product of many terms that appear in your Hamiltonian. So first you reduce your graph to just the spanning tree, and then using this trick of conjugating your product with permutation operators, you can convert the product into a product that would correspond to a 1D graph. So it's kind of technical, but the point really is that using this sort of AMGM inequality, but for matrices, and using a nice trick with permutation operators, you can relate any spanning tree to a 1D graph, and then use the known results for the 1D graph in place of for your results to get upper bound on the circuit depths. The other method is kind of easier to explain. You have a Hamiltonian, you square the Hamiltonian, you get some bad anti-commutator terms, you want to get rid of those. So what you do is you define a new operator, you call it A, which is just sort of the Hamiltonian on a few sites coming out of a vertex. And then you just rewrite the bad terms in terms of the new operator squared and the old Hamiltonian H. And just basic algebra gives you a lower bound on the spectral gap. But for this method to work, you need to find numerically what is the spectral gap of a Hamiltonian on a graph that looks just like the one colored in red. Once you do that, the bounds come straight through. So these are techniques in the physics literature that we use. But this year, many things happen, and this is probably the most important sort of message that I would like to give out to everyone. Is I've compiled the results that have that came out this past year, and as you can see, there are quite a few, and these are the ones that directly relate to what we were doing. So let me just quickly walk you through these. So we have a 1D normal architecture, and brickwork or parallel just means that you can put many gates in the same layer. That was improved to, the improvement came in the K dependence, which became linear from what was previously K to the 5. Then there are other variants of this, which are not really the random circuits in the sense that I define them to be. And there you can get logarithmic in n dependence. So those are really not random circuits in the sense I define them to be. Right? Those are contrived examples where, yes, you apply random gates in a very specific manner, and that allows you to get this logarithmic in n dependence. The complete graph architecture had only a minor improvement. Well, the improvement came in the K dependence again and got rid of a log n factor, but that's the best we still know. And the d-dimensional lattices had similar improvements, but from the results, from our results, we had for arbitrary connected graphs, we need n to the log n. We had an n to the log n dependence, but that was improved to n to the eighth. So that was a major improvement over the known results. But it's not that our work is completely useless now. So there are still simple classes of graphs where our results combined with some of the recent results are the state of the art. So take some connected graph, look at its spanning tree, and see if its degree is constant. And then our results combined with this result tells you the best bound that we know so far on the circuit depth to form designs. And for some common sense spanning tree graphs, which are not too deep and have some constant bounded degree, our results combined with the previous, the new results also are state of the art for those kind of things. So takeaway is random quantum circuits on fairly general classes of graphs. In fact, almost all connected graphs give us unitary designs in short depth, poly-n depth. This result supports quantum advantage experiments in terms of random circuit sampling on arbitrary geometries. We can show complexity growth on, again, any arbitrary connected random quantum circuit. And for certain specific models, which are not random quantum circuits in the sense I define them, we can actually do better than poly-n dependence. We can get log-n dependence, which is the content of the new results. But what remains open is if you just pick 2 qubits at random from your geometry, you pick a random 2-qubit gate, and you compose a circuit in this manner, we don't even know if, so far with all these results over 8 months or so, we still don't have a clear answer if the complete graph architecture, or we have not been able to prove that random circuits on a complete graph gives you designs faster than that on 1D graphs. So that's still open. Only in very contrived examples do we get anything, any improvement on this result. But for the simplest case of random quantum circuits, we still don't have these results. So that I leave as the open question, and thank you for your attention.
Any question?
Hi, thank you for the talk. So I have just one naive question. So is it interesting to look at random unitaries generated by random Hamiltonians in this setting or not?
That is, I think it has been sort of looked at, so it is interesting. It has improved, so I didn't put it in these slides, but if you look at some of the papers by Qifeng Chen over the past, I think in February and April, they did consider like random unitaries constructed from random Hamiltonians. And there they're able to show by Hamiltonian simulation that you can improve upon the k-scaling in some of these bounds. So it has been studied, but if you're saying more like if you want to replace every gate by e to the IHT, I don't think that has been studied, yeah.
Okay, so considering every local unitary is generated by random Hamiltonians, generic ones or some of random Hamiltonians can be interesting to look at.
Sure, yeah.
Okay, thank you.
Any other question?
Hi, are there lower bounds on the depth that you need?
Yes, we do have lower bounds, and those are counting argument lower bounds. I think the lower bounds are both sublinear and N and K. But again, since there are so many different models of random quantum circuits, I'm not sure if one lower bound holds for the other. For example, in the recent paper with where they improved the scaling of forming designs to log n, they have to come up with their own sort of lower bound that is in fact optimal and you can't do better. That's because their model is different from the ones that we study. But the ones that we study have lower bounds were given by Brandau and Hordek. Yeah.
Thanks.
Other question? So your upper bound is for random circuit.
That's right.
And so this means your value is some expectation value over this randomness?
Yes.
Oh, okay.
Yeah, we are finding expectation. So the channel that we are finding the difference between is like here. The expectation value is sort of like incorporated into the channel definition, and then we are finding the difference.
Yeah, but so if I understand correctly, you calculated some upper bound of circuit depth, and that depth is just expectation value over chosen circuit.
Oh no, the depth is depth itself is not the expectation value of anything. It is like a clear number beyond which, if you pass that threshold, then for sure you get this exponential closeness.
Also, here you use the operator norm instead of this diagonal norm, and how they are related?
By just worsening of this factor, this goes to 2.
Okay, so your upper bound also shows some upper bound for this diagonal.
Exactly, yes, that's right.
Any other question? Okay, so if not, let's ask the speaker again. Now we have a coffee break.
Thank you for coming. I was sweating. Oh.
Are you still working on this? You may know that Marco is also interested in this kind of stuff.
Yes.
Do we have the presenter of the second talk? Quite a choice here. Yeah.
Okay.
Okay, so welcome everyone. Welcome to Wednesday 2B session. Okay, and so the first talk of the session will be given by Kuo-Chin Chen on quantum complexity of testing sign and graphical stability. So please.
Thanks for the nice introduction, and thank you all for coming. And I'm Kuo-Chin Chen. I'm from Hong Hai Research Institute in Taiwan, and it is a joint work with Min-Hsiu Hsieh from Honghai Research Institute, and Simon Apers from IRF in Paris. Okay. So let's begin with the outline. First, I will introduce the problem, the clusterability testing problem, and I will show our two main results. The first result is that we provide a quantum algorithm to solve the testing problem. And our second result is that we provide a classical query low bound for this problem. So let's begin the first part. So sign graph. What is a sign graph? A sign graph is a graph whose each edge is assigned positive or negative. As we can see from this figure, we use the green line to indicate the positive edge and use the red line to indicate the negative one. And if we have the sign graph, we call this graph is classical if we can decompose it into several components, such that the positive edge connects vertices in the same component, while the negative one connects vertices belong to distinct components. So as we can see, this graph is classical. However, if we change the sign of single edge, then the graph becomes non-classical. That is to say, if we would like to learn the clusterability of a sign graph in an exact manner, it is necessary to make a big of n queries to the graph, since we have to learn the information of all edges. So the question is that whether we can do better in sublinear time in an approximated manner. So this is the graph property testing problem. So we call the randomized algorithm for solving this problem as the graph property tester. And the tester takes two inputs. The first input is the query access to this graph. And since we are considering the bounded degree query model, so we can make a query access to the adjacent list. And we denote the maximum degree by D and the number of vertex by capital N. And the second input is an error parameter. We call it epsilon. And the target of this tester or this randomized algorithm is to determine the given graph is epsilon far from this property or not. So the epsilon far from this property means that we have to remove or add at least epsilon ND edges to make this graph satisfy this property. And in this case, the algorithm return reject. Otherwise, for example, if the graph satisfies this property, or we just have to remove very few edges to turn the graph satisfy this property. In that case, the algorithm return accept. Okay. And okay, here I show some previous work and the open problem. We take the two famous graph property as example. We can find the bipartite testing and expander testing. The classical query complexity is settled by Goris and Dana around 20 years ago. And Embanus, Charles, and Liu proposed the quantum algorithm for this testing problem and claimed the quantum advantage. And the quantum algorithm have the time complexity for the quantum algorithm is n to the 1/3. However, for the clusterability testing, we got limited work on that. Adrians and Apers provide a classical algorithm to test the clusterability. and the performance is square root of n. However, we do not know the classical algorithm is optimal or not. And furthermore, we do not have any quantum advantage on this problem. So our contribution is, first, we provide the classical query law bound, which implies this classical algorithm is near optimal. And our second contribution is we show a quantum advantage for this problem by providing n to the 1/3 quantum algorithm. Let's begin with the first part, the algorithm. Okay. We begin it by introducing the classical clusterability tester proposed by Simon in 2021. And okay, the algorithm is simple. First, the algorithm have to select a vertex in the graph and implement square root of n random walks from the vertex. And the edge in the walks is positive, and the length of each walk is polynomial of inverse the precision parameter. And the algorithm, the tester aims to find a negative edge connecting the positive walks. And once we found such a negative edge, the main theory of this paper show that okay, the graph is epsilon far from classical with high probability. And we actually turn the classical quantum algorithm into the quantum one by replacing the finding procedure by the quantum collision finding algorithm, and therefore we have the quantum advantage on so we can outperform the classical algorithm. And the result is we got n to the 1/3 query complexity outperform this classical one. And for the second part, I would like to introduce the classical query law bound. So this is the main theory. Any classical clusterability tester requires at least square root of n queries. So this is the main theory of this work. In order to prove this query law bound, the idea is to design a hard instance. So the hard instance contains two sets of graph. One is G1 and another is G2, such that okay, all the graph in G1 are classical, and most graph in G2 are epsilon far from classical with high probability. And we know we have two set of graph with very distinct clusterability property. And in the following lemma, we will show that G1 and G2 cannot be distinguished within square root of n queries with high probability. And of course, in classical, in a classical machine. So let's begin the first part, the lemma, the first lemma. Okay. To begin with the first lemma, let me introduce what's the graph in G1. Okay, the graph in G1, each graph in G1 contains capital N vertices, and the capital N is an even number, and we can assign the parity for each vertex. It can be even or can be odd. And that's for the vertex set. And for the edge set, the edge set contains 3 edge subsets. Okay, and for the first edge subset, it is a Hamiltonian cycle with negative edge. And there is one constraint for the Hamiltonian cycle. The edge can only be allowed to connect vertices with distinct parity. So this is the constraint for the first edge of set. And for the second edge subset, it contains two perfect matching, which means the edge can connect to exact two vertices, okay, for each vertex. And all of the edge in the second edge subset is positive. And we have one constraint for this edge set. The edge can be only allowed to connect vertices with the same parity. And we have the same setting for the third one, okay? And we can see that the graph in G1 set are all classical, since we can easily decompose the graph in G1 into two components, and each component contain a vertex with the same parities. So it satisfies the definition of clusterability. So we have our statement here. Okay, every graph in G1 are all classical. And for the G2, for the graph in G2, we have a similar setting, except that we do not assign parity for each vertex. And we make a change on the sign of the edges. For the first edges, for the first set of edges, it's also a Hamiltonian cycle, and they are all positive. And for the second one, they are all negative. They are and it contains two perfect matching. And for the third one, they are all positive. Okay. And we would like to show that a graph satisfied in this setting are far from classical with a high probability. Okay. Next, we will show how to justify it. But we can first observe that every graph in G2 is not classable. Why is that? Since we have to consider if we consider the set of graph, the set of edge E1, it is a positive Hamiltonian cycle, and it connects each vertex into one component. So yeah, for each graph in G2, we can only have one component when we considering the clusterability. However, we have the edge set E2, so which means we have one component and we have a lot of negative edge in the component, which violates the definition of clusterability. So in order to make the graph classical, we have to remove some edge in E1 or the cycle edges. Since we do not really have to consider removing the negative edges, since if we would like to do so, we have to remove all of them, right? So now we only consider removing some edges in E1. So since we cannot remove that many of edges in E1, we can remove at most epsilon ND edges in E1. So it will induce epsilon ND components on the cycle. So, and next we would like to consider the third set of edge, E3. We can show that even if we remove that many edge in E3, okay, the E3 connects this cycle component with high probability, which means if we only consider the E1 and the E3, we can only have one component, even if we remove that many of edges from E1 and the E3. So the graph in G2 is far from classical with high probability, and the first lemma follows. So next, I would like to show the no classical algorithm within square root of n queries can distinguish the graph in G1 and G2, and of course with high probability. So what do we mean distinguish? First, we sample a graph in G1 or G2 uniformly. And the algorithm could make a query to the sampled graph, and which means the algorithm could learn square root of n edges from the sampled graph. And then there are two conditions. The first condition is that we cannot find any cycle, which means the algorithm cannot distinguish G1, the graph is in G1 or G2. Seems okay. For each query, the graph always answer a new vertex. So in that case, of course, the algorithm cannot say anything about the graph. Okay. And for another case, if we can find, so if the algorithm can find a cycle, and we can show that the probability for this case can be bounded by 1/10. It's quite similarly to the collision finding. And yeah, with this observation, we have this lemma. So in summary, combining this lemma, we have the desired classical query law bound. And I give a brief summary and the open problem. First, we of course we claim the quantum advantage on testing clusterability, and which means no any classical algorithm could outperform the quantum algorithm as mentioned. And a natural question is that the quantum algorithm is optimal or not. And the answer is we have no idea, since we do not have quantum query law bound for the clusterability testing problem. According to previous literature, we can find one for expander testing, and the query law bound is n to the 1/4. And of course, it is not tight, since the best expander tester can the query complexity n to the 1/3. Therefore, it is not a tight lower bound. So I think that's all. Thanks for the listening.
So thank you for interesting talk. So any questions? Okay, so I have a question. So you study clusterability problem, and so you don't care about the number of clusters. Does it make any sense to maybe some limitations on the number of clusters that you are introducing?
You mean the definition of the clusterability?
Yeah,
right?
just a different problem when you have.
Yeah, we don't care how many cluster we can build, but once we can, of course, there can be many cluster proportional to capital N, of course. Mm-hmm. But once we can find such a cluster, then it is clusterable. Yeah.
Okay, thank you. So maybe any questions? Okay, so if no questions, then let's thank the speaker again.
Okay, thank you.
So is the second speaker present? Okay, that's you.
Oh, sorry. No.
Yeah, just once. No, it should be
Yes. Good.
Okay, so it's 11. Let's continue. So the second talk is given by Xavier Coiteux-Roy, and so it's about distributed quantum advantage for approximate graph coloring. So please.
So hi everyone, I'm really happy to be here to present you this result, which was the outcome of a rather large collaboration. So I first want to thank all of my co-authors, Francesco D'Amore, Rishikesh Gajjala, Fabian Kuhn, Francois Le Gall, Henrik Lievonen, Augusto Modanese, Marc-Olivier Renou, Gustav, Schmid, and Jukka Suomela. So the conclusion of this work will be that the speed of light bounds the speed of quantum distributed computing. And the model that I will present is mainly a model of quantum communication. So now it might seem obvious at first sight that the speed of light will bound the speed of quantum communication. However, the conclusion of the last decades of research in quantum information tells us that this is not so obvious. One example is that non-locality, quantum non-locality, can, in some special case, replace communication. Maybe the best example of this is pseudo-telepathy, so a form of Bell inequality, for example, the magic square game, that can be won without any communication. There are also results that generalize what we can do with quantum non-locality. So they generalize quantum information, but still imposing causality. And we have results like, for example, the one by Van Dam that says that for bipartite distributed computing, the complexity collapse in presence of super strong non-locality. So for this reason, it's not trivial to find bounds on what imposed by causality in networks. And today I'm going to present you some no-go results. And they will be obtained by combining two lines, two directions of research. On one side, we will have no standing bounds that comes from causality or the speed of light that will impose constraint on what networks of quantum computers can do. On the other hand, we will have fast classical algorithms. And this will create a sandwich. And by bringing these two lines of work close together, we'll be able to rule out quantum advantage. So today we'll focus on the part that is the no signaling bound and on the model. But there's a lot of our work that is also about this classical algorithm. And for this, I refer you to the paper. Especially if you're interested in graph theory, there's some cool techniques. So what's graph coloring? Graph coloring is this very natural problem in computer science where you have a graph here. It's going to be a graph of computers. And they want to output some colors such that computers that are neighbors have different colors. So more precisely, we can look at, for example, C coloring of key chromatic graphs. So we have C colors available. And the minimum number of colors that is needed to color the graph is key. For example, we can 2-color cycles or 3-color grids or 25-color bipartite graph. Now, one way to color this graph of computers is to elect a leader, give him all the information about the graph, have the leader compute a solution, and then distribute it, communicate it to all parties. This works well if the graph is small. But if we're thinking about a bigger graph, then this means that the speed of the solution will be bound by the diameter of the graph. So instead, we're going to try to get an approach where we want to obtain a global coloring, a global solution from only local information. So basically, we want to have that every computer in the graph has just some knowledge about its surroundings, its neighborhood, through communication and a short range, and so that they can come to a local solution that is also a global solution. So more specifically, the model that we're going to study is the local model of distributed computing. And it works as follows. I'm going to illustrate it on the line now. So I have 4 computers. So each node is a computer on a graph, and they have unique identifiers. They have unique names. Now the algorithm is going to proceed in T synchronous round of computation and communication. So the computation is going to be local, and the communication is going to happen by passing message to your neighbors. So everyone at the same time is going to send message to all of their neighbors. So there's going to be computation step, then communication step, then there's going to be another computation step, another communication step, and then at some point, the nodes will output a solution. What we're interested in is the complexity, which is the minimal number of rounds of computation and communication before a solution is reached, a proper solution is reached. In the local model, the computational power is unbounded locally, and the bandwidth, so the size of the message that can be communicated, is also unbounded. So what I've introduced you is the deterministic model. In the randomized model, it's basically the same thing, but the players are allowed to flip coins to have some private randomness. Now I'm going to tell you about 2 other models. One will be the quantum, and then the no signaling model. So this is basically the roadmap of the variant that I'm going to approach today. So what's the quantum model? First, we can consider with or without shear entanglement. Our results apply in both cases, so let's just consider that they do have shear entanglement. So now the quantum local model is going to be similar to the classical one, but we replace local computation and communication by quantum computation and quantum communication. So the players are allowed to do some unitaries, and then they do some communication, then they do some other unitary, some computation, and then at some point they measure. It might be insightful to view this as a circuit. So here I'm going to redo it, but with a circuit. So we start with the states of the different nodes. Then they all do this unitary. So since they have access to shared entanglement, we don't lose generality. So they apply these unitaries, the communication step, computation step, communication step, and then at some point they measure and they output an answer. Now, if you're familiar with circuit complexity, you know that there is a very simple argument we can do in this type of diagrams, which are the light cone arguments. So for example, if we have access to 2 rounds of computation and communication, well, we will see that the last output depends only on what is in this orange light cone, and it doesn't depend on what is outside of it. So we can change the structure of this without affecting the outcome here. And this observation is actually quite powerful and can be generalized. And we're going to generalize it to define this no signaling local model. So this model is more to be viewed as a tool that allows us to bound the quantum model. It's not a model that tells us how to achieve some computation, but it tells us exactly what we cannot do. And what we cannot do is to violate the no signaling principle. And what the no signaling principle is that if we take the no signaling algorithm and we put it on 2 different graphs, Well, for any subgraphs of these two graphs that have isomorphic T neighborhood, they will, if they have isomorphic T neighborhood, they will have the same output distribution. So to illustrate it, I have two graphs here. And I consider this neighborhood the subgraph 3 and 2 on the top and the bottom. And I'm going to look at a distance 1 at the light cone. So the 1 neighborhood, after one step of communication, stops here. What this means is that whatever comes afterwards can be changed, and it's not going to affect this probability distribution. So in this case, what 3 and 2 outputs must be exactly the same in both scenarios. And we can apply this principle for every subset, every subgraph of this graph, for every graph over which we run the algorithm. Now you might start to understand where I'm going. If not, here's a last hint. Imagine you're an ant and you are walking on one of these two surfaces. One is a grid and the other is a Klein bottle. And how can you tell on which one you are walking? So our results one of our results concern grid, and it's the easiest one to illustrate. So I'm gonna first tell you about grid, and then I will show you how this generalizes to more graph. So let's say that we want to tricolor a grid in the deterministic local model. So this cheating graph technique that uses this no signaling principle is actually quite old. That's from the beginning of distributed computing. And the argument is as follows. So we want to tricolor this grid. We know that there's a trivial or straightforward classical algorithm that can do it in square root of n, where square root of n is the diameter of the grid. And as you can see, there exists a solution to color a grid. So now we want to bound the complexity of this algorithm. I mean, of the deterministic local model. So for now, we're going to forget about this grid, and we're going to look at this odd quadrangulation. So this is the Klein bottle that I was telling about. So we take the grid, we bend it and make a cylinder by gluing the left and right part. Then we twist the bottom and the top. We glue them together and we make this Klein bottle. Now what's interesting about this is that there are some results about odd quadrangulation that allows us to tell that the chromatic number of this is at least 4, which means that if we try to color it with only 3 colors, there is going to be at least one place where there is no proper coloring, even if we have full knowledge of the grid or of the Klein bottle. So here the error is here. Now I'm going to show that if we have only one round of communication, we're going to make also a mistake. There's going to be also a failure in the grid. So we take this neighborhood, we take this unique identifier, and we have that because of the light cone argument that whenever we have this subgraph neighborhood, the two graphs in the middle are going to make a failure. So namely, we can copy paste this into this scenario, and we will have that the grid will make the same failure as the Klein bottle, which means that, okay, this grid cannot be colored in one round of communication. Using this argument with more communication and namely bigger grids, we can show that the amount of communication that is needed to color the grid is the amount of communication that is needed to tell the difference whether it's a grid or whether it's a Klein bottle. And namely, this is the diameter of it. You need to be able to communicate in enough round to be able to talk to the person that is on the edge of the grid. And only then is the impossibility about the Klein bottle not applying on the grid anymore. So this is the argument that gives us a lower bound on deterministic local. And what we've done in our work is we've lifted this argument from deterministic to no signaling model. So I'll make a first stop at the randomized model, which was deterministic plus private randomness. And the difficulty, the first obstacle that we have here is that with this chromatic number 4 of the Klein bottle, we could conclude that there was at least one point where there's a failure. But if the Klein bottle is really large, then the probability of failure at a specific point is very low. So how do we amplify this? Well, it's simple. We use the independence principle that if subgraph has disjoint t-neighborhood, well, they will have independent failure, independent distribution, so independent failure. So each of these nodes will have independent chance of failing, which amplify the result and gives us that, okay, with very high probability, it's not, the grid is not going to be correctly colored. And from this, we obtain the randomized local result, which tells us that the classical algorithm is still optimal. Now I'm going to skip over the quantum and go directly to the no signaling. So in the no signaling model, we have two new difficulties. One is that because we allow a generalization of what is shared entanglement, we don't have this independence principle anymore. So we have long-range correlation in the grid. And because of the extension of the no cloning theorem, we have that if our cheating construction has n nodes, then our graph will, and that we want to color also needs to have n nodes, so we cannot consider bigger graph. But these difficulties can be solved, and we've developed some kind of systematic techniques that involve covering many copies of the cheating graph and then reassembling them into some disjoint regions. I will not give you the details of it, but let's just say that we have a blueprint that allows us to have a systematic argument to build this kind of lower bound. Then we apply it on grids, and we have that this impossibility and this lower bound of square root of n applies also to the no signaling model. So now we have for grid that the lower bound and the upper bound are exactly the same. So the quantum advantage is 0. There's no room for quantum advantage anymore. So this was about grid. Now this blueprint, we can also apply it for general graph. In fact, we've designed it for general graph because the grids, they also have symmetries that people have used to reach the similar results. So this technique about covering the graph we need a cheating graph to be able to apply it. So we need a graph that has this property where locally it looks like there is a solution, but that globally we know that there's no solution. And it turns out that there's a paper by Bogdanov from roughly 10 years ago that does roughly what we want. And you can see from the title, examples of topologically highly chromatic graph with locally small chromatic number, that it's very relevant. And it turns out that we can apply this technique through a slightly modified version of this graph. And we obtain that for C coloring key chromatic graph, there is a classical algorithm. And so we obtained this lower bound, no signaling, that is n, so the alpha root of n, where alpha is c minus 1 over key minus 1, which looks arbitrary, but since it's tight, turns out that it's the right answer. And we have a classical algorithm that does it in the same asymptotic, that reaches the same asymptotic value up to some polylog factors. And then this factor depends whether we're in the randomized the classical randomized version or the classical deterministic version. But I haven't told you anything about this classical algorithm, which is the other part of our paper. So we have characterized fully the hardness of approximate distributed coloring in general graph. So in particular, if you want to three-color bipartite graph, you have that the complexity is roughly up to polylog factors, it's theta of square root of n. If you want to four-color bipartite graph, we have that the complexity is up to polylog factor theta of cubic root of n. And if we want to 25-color, 7-colorable graph, well, it's n to the 1/4. So now this is solved, but there's still some open problems. One is that we've developed this technique and this blueprint to be able to find bound on quantum distributed computing from causality. And our technique doesn't apply only for coloring problems, but for any locally verifiable problem. So locally verifiable problem on graph is a problem for which the solution can be checked by looking only at the local neighborhood. So for example, for coloring, it's sufficient to check that every pair of nodes have different colors to conclude that it's the right solution. So now we could apply similar technique to other locally verifiable problems and hope that the sandwich is tight. But this is not always the case. And my favorite example is this very simple one, where we take an infinite line and we have three colors and we want to color it in finite time. Or said in other words, we can try color cycles. And the complexity of this for the classical algorithm is log star n. So log star n is smaller than our up to polylog factor, it's quite small, but it's not constant. However, there is a solution that belongs to the no signaling set that is constant, that is actually 2 rounds. So now the question is, okay, well, where does quantum fit inside this? And this class of problem that has this complexity log star, they're actually quite fundamental in distributed computing. So this is an important problem. It's not just an edge case. So to recap, I've introduced the local model of distributed computing. I've talked about the coloring. I've told you that there were 4 variants that were from weakest to strongest in this model. And that our argument came from combining fast classical algorithms and no signaling bounds and finding that when they match, there's no quantum advantage. And that these no signaling bounds, they mainly came from adapting this local indistinguishability argument to the no signaling scenario. And from this, we conclude that we've characterized the hardness of approximate distributed coloring up to polylog factors. So thank you very much for your attention. I'll be happy to take questions.
So thank you for your very interesting talk. So any questions from the audience?
Hi, thank you for the great talk. I guess a natural question for me was what happens if you bound the amount of communication that happens between each node or parties?
Yes, if we bound the amount of communication, the other main model of distributed computing is called congest, and it does exactly this. And then there's a bit more result in congest than in local concerning quantum advantage, mainly because we can do things like Groover's algorithm in networks.
Okay, so do you think there is a possibility of advantage over there in the congest model for this problem?
Yes, I think that there is advantage over there.
Oh, okay, thank you.
So any other questions?
But I'm not sure it's for coloring. I didn't study coloring.
Okay, I have a question myself. So your talk was a bit pessimistic one, so it shows there is no signaling advantage, let alone quantum advantage. Where should we look to get quantum advantage in this area? Like which kind of problems we should look at?
Yeah, so at the moment we're doing exactly this, trying to find where we can find quantum advantage. And at the moment, what looks quite promising is to apply idea from network non-locality to have some non-local games, and from this we can at least get proof of principle of quantum advantage. What was nice about this work was that it was a very natural problem, coloring. So now what we would really like is quantum advantage for natural problems, and I cannot prophesize yet where it will come.
Okay, thank you. So maybe any last questions? Okay, if no, then let's thank the speaker again.
Testing.
Okay, let's continue. And so the last talk of today is given by Eric Culf. And so new approaches to complexity using quantum graphs. So please.
Thanks for staying for the last talk before the excursion. So I'm presenting some joint work with Arthur Mehta, who's at the University of Ottawa, and we're studying a complexity problem that's related to quantum graphs, and it gives an interesting collection of complete problems for some well-known proof classes. So I'll give an overview of the complexity classes involved in this work. So the most basic one is when you just have a classical computer presented as a Turing machine, is what can you do in polynomial time on this? It's the class P, and then there's the proof version of that. When you, there's the random version of that, which is BPP, a bounded error a probabilistic polynomial time, and then the quantum version BQP, which is when you what can you do when you have a quantum computer running in polynomial time. These can be augmented with classical proofs. So there's a prover who gives an extra classical piece of information that for a yes instance should always should help the verifier to learn that it is a yes instance, and in a no instance, no proof should fool the verifier into thinking that it is in fact a yes instance with high probability, and that this gives the classes NP classically, MA for randomized classical, and QCMA for quantum with classical proofs. In the quantum case, there's a few potentially larger classes that are alternate versions of a proof class. QMA, which is where the proof is a quantum state and not a classical string. And then the main focus of this work is on QMAK, where instead of assuming that there's one quantum proof, the prover gets multiple quantum proofs, or the verifier gets multiple quantum proofs, or alternately, the proof state has partitions across which there's a guarantee of having no entanglement. So an important result on QMA2 is that it's in QMAK is that it is in fact the same thing as QMA2 for any polynomial number of proofs. So it really the class is the difference between QMA and QMAK is just, is there one proof or are there two proofs used to prove the language. So QMA2 is so what is known about QMA2? It's was introduced. One idea is that it should give some idea of the power of unentanglement. How much knowledge extra knowledge do you get if you know there is no entanglement at a certain point in a state? But in terms of complexity theory, not too much is known about the relationship of QMA2 and its neighboring classes. In particular, it's known to contain QMA, and it's known to be contained in NX, but no tighter containments are known. Further, thanks to the QMAK equals QMA2 proof, it's known that the QMA2 can be you can assume that you have exponentially good completeness and soundness, and there are complete problems known for QMA2, but they are perhaps less natural than the complete problems known for example, QMA. The known complete problem for QMA2, the closest to the local Hamiltonian problem for QMA is the separable sparse Hamiltonian problem. It's asking that when you're given a Hamiltonian that's represented as a sparse matrix, is there a separable state with low energy or not? However, the more similar to the local Hamiltonian problem, the separable local Hamiltonian problem, given a local Hamiltonian, is there a separable state with low energy? That problem is in fact in QMA, not in QMA2. So that it sort of begs the question: is this separable sparse Hamiltonian problem really the generalization of the local Hamiltonian to QMA2? And if not, is there a problem that naturally gives both complete problems for QMA and QMA2 with some variation of the parameters involved? So that's what I'm going to be talking about today. It's a problem that comes from quantum graphs, and as we know, the graphs are a very liquid, very good source of problems in complexity theory. And one thing you can do is you can give a graph as the problem instance and ask, what are some properties that this graph has? For example, very important for this work is the clique problem. Given a graph, does there exist a subset of vertices where all the vertices are connected to each other? Closely related is the independent set problem, which is sort of the converse, that given a graph, is there a set of vertices where none of them are connected to each other? And also closely related is coloring, where the goal is to partition the graph into a certain number of independent sets. So for a given clique size, asking is there a clique of this size isn't P, because you can just cycle through the vertices of the graph. But given both the graph and the wanted clique size as input to the problem, that does become NP complete, and that's a famous early NP complete problem that was known. And in this work, we look at a different way of constructing graphs, and it comes from channels. So classically, a channel is just a probabilistic map that to each point of an input set associates a probability distribution over the output set. And a graph that can be constructed from this is the confusability graph, which just says that if two inputs are possible to be confused by the graph, by the channel, they should be connected by an edge in the graph. And so for example, this given some channel where these arrows point to the different outputs that you can get, you can construct the corresponding confusability graph. For example, the fact that both x1 and x2 map to y1 means that x1 and x2 should be connected by an edge in the confusability graph. And a fundamental theorem on the confusability graphs due to Shannon is that the zero error capacity of the channel, how much information can you send through this channel without any probability of error, is the size of the largest independent set of the corresponding confusability graph. So there's a connection between communication with classical channels and the corresponding confusability graphs. And we can use this idea to talk about graph parameters for channels, and use this to come up with complexity theoretic problems. So that's the question we're interested in is, given some channel, can we talk about the complexity of computing the graph parameters of the corresponding confusability graph? So classically, in the deterministic case, this is the same thing as the collision problem for functions. Given a deterministic function, are there a pair of inputs that give the same output? And it's known that this collision problem, which is equivalently phrased as the two clique problem for the deterministic functions, is an NP complete problem, and it can be seen as a graph problem on a succinctly presented graph. Similarly, you can sort of come up with a probabilistic version of this that becomes MA complete. Here, it's we use a notion of confusability that has a little bit of a robustness parameter alpha that says that the two inputs should be connected if there's a probability if the probability of confusion is above a certain threshold. And with this notion of connectivity, this problem also becomes MA complete if we're quantifying over classical probabilistic channels. Now, to get a quantum version of this problem, the the first thing to do is ask how should these graph properties of classical channels be turned into graph properties of quantum channels, and this is done via the idea of a quantum graph. So given a graph, a different way to write the graph rather than a drawing is using the adjacency matrix, and equivalently the adjacency matrix can be associated to something called an operator system, which for a classical graph is just the vector space of matrices where you just fill in every place in the adjacency matrix that has a 1 or is on the diagonal with an arbitrary complex number. So formally, an operator system is just a vector subspace of the matrices that's closed under the Hermitian conjugate, and it contains the identity operator. And this is the sort of the right object to generalize to get a quantum notion of a graph, because all of the classical graphs are contained as operator systems, but there's more operator systems than the ones constructed in this way, giving natively quantum graphs. The sort of justification for why this is the right notion of a quantum graph is that these confusability graph ideas can be directly generalized to a confusability graph for quantum channels, and it's just a span of the products of the Krauss operators gives you an operator system, and this operator system has connections to the zero error capacity of the corresponding channel. As for a quantum graph, as for a classical graph, I mean, you can look at cliques and independent sets of quantum graphs. A clique is just a subset of vectors such that the corresponding ketbras of vectors are contained in the operator system, and an independent set can similarly be phrased as a set of vectors where the corresponding ketbras are orthogonal to the operator system. So using this idea of quantum versions of cliques and independent sets, we can look at how this gives a quantum clique problem for channels. So again, we want a bit of an error-robust version of this notion of a clique, and here we look at it as we look at a clique for a channel as states, rho and sigma, that are orthogonal, but once you pass them through the channel, they have high overlap. And this gives a promise problem, which is the problem we want to consider, which given a channel, say via its circuit description, we ask whether there exists a clique with a certain parameter, or with a completeness parameter, or a no clique up to a certain soundness parameter. So a major result of our work is to show that this problem is actually in QMA2 with any inverse polynomial completeness soundness gap. And the way to do this, is making use of the swap test. So the proof, the QMA2 proof is just the tensor product of the two states that form the clique. The way this proof is verified is that one of two things is done by the verifier. The verifier does the swap test on the two input states to check that they're orthogonal with a certain probability, and the rest of the time the verifier acts with the channel on both of these states and does again the swap test to check that they have high overlap. So QMA2 is potentially a very large class, and it's not really that interesting to show that a problem is simply contained in QMA2. The main result of the work is that we show that this problem is hard for QMA2 as well as being contained, so it's QMA2 complete. The idea is that we will make use of the structure of cliques for partial trace channels, and essentially this will allow us to guarantee separability of the states in the clique, and then also use cliques of entanglement breaking channels in order to guarantee some properties of the QMA2 verification circuit. So an entanglement breaking channel is just a measurement followed by a state preparation, and the way the hardness proof for this problem works is that a QMA2 proof, which can just be seen as the tensor product of two states, is encoded as a two-clique as just you take this tensor product and you tensor on another qubit, which could be 0 or 1, in order to guarantee orthogonality of the two states in the clique. And as I mentioned, the channel constructed to show hardness makes use of a partial trace first to enforce the separability of the states in the clique, and also an entanglement breaking channel to verify that the states actually both give proofs that accept with high probability. Finally, this a restricted version of this problem can be used to also give a QMA complete problem. And the way the problem is restricted is just to consider only entanglement breaking channels, and it's just a very large subset of these entanglement breaking channels as the class of channels to quantify over, and the subset is just those that forget one of the qubits in order to avoid having to check orthogonality, which would require a swap test. And it uses two important results. One is from the work of Baigi and Shor on a related problem, on a related complexity problem to this quantum clique problem. And there they show that given a local Hamiltonian, there is an entanglement breaking channel where these maximal overlaps scale inversely with the ground energy, and then that gives you that entanglement breaking channels are in fact hard for a QMA. On the other hand, there's a theorem of Brandao that gives a class of QMA problems QMA2 problems that are actually in QMA, and then these are the QMA2 problems where the verifier can make a Bell measurement, that is, measure locally on the two factors of the proof, and then do classical post-processing on the measurement results to decide whether or not to accept. And it turns out that doing the swap test on the output of an entanglement breaking channel is actually a Bell measurement, and thus the verifying this QMA2 proof for the clique problem is actually something that can be done in QMA. In conclusion, the quantum clique problem for quantum channels, it gives by changing the set of channels over which the problem is quantified, it gives a variety, gives complete problem for a variety of interesting proof classes. I think there's quite a few open questions available for study in this direction. First is something I didn't mention earlier, but I did mention that there's this idea of independent set, and there's an equivalent problem for independent sets. And what we know is that for the problems corresponding to NP, MA, and QMA, the same hardness results hold, and we know that the quantum independent set problem is contained in QMA2. But the proof techniques we use for the QMA2 hardness actually break down in the independent set case. So it remains to be shown whether the quantum independent set problem is QMA2 hard or not. The other graph problems could be adapted in this way to give perhaps interesting complexity theoretic problems for quantum channels. Another class that I mentioned that could be of interest is QCMA, with classical proofs, and there might be some construction of a problem from this class that gives a complete problem for QCMA. Finally, there are, other than these classical graph parameters for quantum graphs, there's also quantum graph parameters for quantum graphs related to related more closely to non-local games. And there could be a way to talk about these parameters for quantum channels and get interesting complexity problems from those. Thanks for listening, and I'll open up for questions.
Okay, thank you for your interesting talk. Any questions, please?
Were
there no known QMA2 complete questions before?
There were known problems. The one I mentioned is this sparse separable Hamiltonian problem. But the way that, as to the best of my knowledge, the way the known QMA2 complete problems relate to QMA complete problems was sort of unclear, and I think this problem gives sort of a natural problem that you can sort of interpolate between QMA and QMA2.
Thanks for the nice talk. Do we know anything if the channel has, say, a succinct description? Then does this problem remain hard, or?
Sorry?
Say the channel has a succinct description. Maybe the cross rank is small, or the cross operators are maybe classically describable. Does this problem remain hard in QMA?
Yeah, I mean the thing that makes this problem hard, or in fact that makes the problem quantum, is that the channels have to be succinctly described. We were using the like circuit description, but I think you can get away with using like a succinct Krauss description and get a problem with a very similar flavor. If you restrict to looking at like full Krauss descriptions of channels, all of these problems end up in NP. I don't know if they're NP hard or not, but because you don't have quantum systems of exponential dimension. You just have quantum systems of polynomial dimension, which you can do classical things with.
Thanks.
Thank you for your last talk. I wonder, in this quantum two-click problem, is this quantum channel given as a black box oracle, or you need to?
It's I mean, you could give it as a black box. We were considering giving it as a circuit, but in the actual proof, it's used. The circuit is just used as a black box. We don't look inside the circuit and see what happens.
Okay. So this hardness from is come from this hard random oracle or some quantum circuit is also okay.
I believe so, but we can talk after if you'd like.
Okay.
If you give it as a black box, do you think it's useful for maybe oracle separations, like quantum oracle separations, QMA to QMA?
Maybe, yeah. I hadn't thought about that, but yeah, maybe there's a way to sort of spin this as an attempt to do an oracle separation.
Thanks.
So, any more questions? Okay, so what's the last? Okay, so if there are no more questions, let's thank the speaker again and call it a day.